Did I turn is the mic on? Okay. Dear Father, we thank you for this day. And Lord, I thank you for these students and just ask you to bless this time. Just help us to glorify you, Lord, in what we do. In your name I pray, Lord Jesus. Amen. So I was thinking, let's just fiddle around with how should we understand algebra valued forms, and can we do something with them? Let's just play with that for a couple minutes, and then I'll use the projector and read through my paper. It'd be very exciting. But so what should an algebra valued form look like? First of all, I'm thinking of algebra. What was that? Was that just me, or did you guys see the lights flickering? Oh, okay. So algebra valued forms on A is my idea. And of course, A, as usual, a commutative, unital, associative algebra over the reals. So, to start with, zero form would look like what? Just be f, right? A function from A to A, right? That'd be the natural zero form. AKA what I usually call CA, right? A differentiable functions on A. Then what would a one form look like? My thinking is it should be essentially something, calculationally at least, something of the form, say, alpha 1 dx1 alpha n dxn, right, with alpha 1 through alpha n coefficient, a differentiable functions, I would think. I think this is probably the same as just taking the tensor product of the usual real-valued differential forms with CA. I think of what I'm describing is essentially it's just CA tensor the usual forms over A. That's the starting point of my thinking anyway. So I'm just going to basically swap out the real functions for algebra valued functions and let the differentials behave as usual. So what's a two form look like? We could do something like the sum over I less than j, beta ij dxi wedge dxj, right? With beta ij, you guessed it, yeah. And likewise, if we're talking about a k form, gamma, something like the sum over I and the increasing indices of length k taken from n, of gamma I dxi with gamma I a differentiable functions. So I think it's relatively clear that the usual algebra plays nice with this construction, right? In the sense that if we have what rules do we have for alpha, beta, gamma? And I need to come up with some name for this thing. Let's say A valued forms on A. I'm just call it omega A for the sort of the natural exterior algebra here. Then, how should that go? Something like if we also have functions, right, like f and g in CA, right? Then I would assume we're commutative algebra too, right? So if I had something like alpha wedge f beta, I can pull f out, right? And to be more true to my usual notation, I probably should put stars. But, like this is the But I'm not going to do that because it's just too many stars. We already got wedges. Wedges and stars. It's too much. It's too much. I can't do it. But I think we should be able to pull, I mean, that would assume that would be part of aspect of this construction. We can pull functions out. Certainly, we ought to have the usual song and dance. Right? The wedge product should be associative. It should be skew commutative. Is it sum or product? I can't remember. All of a sudden, sad. You think about that. Is it the sum or is it the product? Sum, right? Sum, yeah. P plus Q. So example, for one forms, we have alpha wedge beta is minus beta wedge alpha. Whereas forms of even degree commute with the rest of the exterior algebra, right? Anything else I should think about in terms of basic algebra? Alpha wedge alpha should still, yeah. I mean, I think if alpha has odd degree, right, say k, and then alpha wedge alpha is equal to minus 1 to the k plus k. Ooh. Is that right? That's not right. You guys sold me a bill of goods. It's the product. I was right to start with. One times 1 is 1, so like 1 form's anti-commute. 2 times 1 is 2, which makes that sign. Anytime one of the form degrees is even, that product is even, so minus 1 to an even number is 1. You need odd times odd to get minus 1 there, which it's product. So this is odd degree, so is the product of odd and odd odd? Product of odd times odd odd? It's odd. Yeah. Proof by example. You guys are a hoot. All right, so that's minus alpha wedge alpha. So as long as we're working in characteristic 0, and we are only working in characteristic 0, because, well, I don't have enough patience for other characteristics right now. You know? My calculus is very characteristic 0. I mean, is there calculus for other characteristics? Well, of course. But yeah, so in short, Jess, yeah, alpha wedge alpha equal to 0 for alpha odd degree. Now, for even degree, there's no reason that an even degree, like a 2-form wedge, a 2-form doesn't have to be 0. In fact, interesting equations of theoretical physics are built from taking wedge products of 2 forms with themselves to construct actions and so forth, yeah. Well, I think that's about it for that. Then you start thinking about exterior derivatives, right? That's where it might start to get interesting. You know, what would df look like? I mean, it should be what? I mean, it should be I would assume it should be the sum, basically, I equals 1 to n, partial f, partial x, I, dxi, right? But then if we're assuming that it's a differentiable, that means a little bit more, doesn't it? What's that mean? That means this has actually the form, you know, partial f, partial x1, the sum, I equals 1 to n vi dxi, right? Oh, I wrote my i's up somehow. I still haven't come to terms with where they're supposed to be. You notice that I've got them. You notice over here I've got down, up. So in my heart they're still up. But I mostly teach math majors, so I get tired of talking about upwards indices. It's an uphill battle. Now, our typical notation would be that this is d zeta, and this is df d zeta. Right? So df is, you know, I mean, we could say, I usually do partial f, partial zeta, b zeta. So how about a one form? What happens there? Then we're looking at the differential of, you know, alpha, the differential of the sum of alpha I dx. Look the i's up again. Woohoo! Equals 1 to n. And so that's, of course, the sum, I mean, by definition, really, that's d alpha I wedge dxi I equals 1 to n. But the d alpha I we can write as what? Using this result, the d alpha I is what? It's partial alpha I, partial zeta, d zeta, right? And so that's going to give me what? I equals 1 to n of, looks like partial alpha I, partial zeta, d zeta, wedge dxi. Zero. I'm afeared it's 0. Well, yes. I guess the question I'm begging is there some sort of something I can write naturally over the algebra here to express the two form in terms of wedges of differentials over the algebra? Thoughts? Multiply by VI and its inverse. Let's see here. Yeah, we could do that. What would that do for us if we did that? I guess you're saying it would create a d zeta. But it's not as bad as that's not automatically 0 though, because the weights don't have to be the same. The partial alpha I, partial zetas, they're not equal across that construction, so you don't actually get the d zeta wedge d zeta like you're thinking. My intuition here is that we ought to be able to write an arbitrary 2 form. We ought to be able to express it in terms of the conjugate calculus. So, we have zeta 2, for example, is x1 minus v2 x2, right, plus v3 x3, plus vn xn, where we're assuming that we're working with an invertible basis. So the second conjugate flips the sign on the second component, leaves the rest alone, and then the third conjugate would unital basis, the identity at the start. So x1 plus v2 x2 minus v3 x3 vn xn, like that, right? So you see you see naturally then what the d zeta 2 should be, right? The indices are down again, well, right, etc. So if you look at something like, d zeta wedge d zeta bar 2, you'll obtain the sorts of things that appear in the 2-form expansion. And I believe in beauty, so I believe that when you sort through that, there will be some sort of beautiful pattern that appears in this construction. But I'm speculating. So let's just look over the most simple thing you could think about, right, would be in 2 dimensions, complex case, right? You guys may have never thought about that before, but if we were working in the complex case, what would a 2-form look like? 2-form would look something like, it's kind of just one, there's just, it's not as exciting as I was hoping for. It's, some constant times, constant function, complex valued function rather, dx wedge dy, right? And then you guys remember the x is equal to what in terms of, it's 1/2? Z plus z bar, yes? And y is, what is it? 1/2i, z minus z bar, yes, no? Yeah. So that means that this actually is going to work out to 1/2 dz plus dz bar wedged with 1/2i dz minus dz bar, right? dz wedge dz and dz bar wedge dz bar are 0, and it just leaves you with, what do you get? You get 1/2 of, 1/2 g dz, dz wedge minus I/2i dz bar, right, plus g/2 dz bar wedge 1/2i dz. And so that's really, how did I get an I upstairs and downstairs? What's wrong with me? I. So that gives me minus Ig/2 minus, looks like, I'm sorry, I can't do math. So G/4, I'm creating extra factors of 1/2. No, I'm not. There's a 4. G/4i, oh my goodness, I'm running on fumes here at the moment. g over 4i dz wedge dz bar, right? And then plus g over 4i. Oh, but I forgot a sign, right? Where was my minus? This one here, right? Yeah. I erased that sign. I shouldn't have. So dz bar, grief. dz bar wedge dz. All right. And so, what do we get? Ig over 4, right? Ig over 4, Ig over 2 rather. Dz wedge dz bar, I think. I put the I upstairs though.
You switched the order of the second component by exchanging the dz bar wedge dz for negative.
Yeah, dz bar wedge dz is minus dz wedge dz bar. They're one forms. Algebra valued one forms, in fact. So that shows you that a two form over the complexes can be written as the wedge product of the algebra variable and its conjugate. I'm on something similar but hideous, more complicated is probably going to be true, as long as we work with an invertible basis where the conjugate variable construction is good to go. But the description of such forms is much more involved, I suppose. I mean, if you study several complex variables, guys, if you look at books on that, something like CN, then there you end up with things like, dzi wedge dz bar j or something like that. And you'll start seeing differential forms referred to by their bi-degree, which is like the number of z wedges and the number of z bar wedges, something like that. So there's a whole nomenclature to deal with this kind of breakdown and what it means for the theory. And if you study several complex variables, there's a well-developed discussion here, an extension of one complex variables to more. There are surprises and there's nuances I don't fully comprehend yet, but anyway. So that's waiting for us. That's one thing, right? If we want to really algebratize the differential forms, that's one big looming algebra problem. And, I suppose one of the exciting things for us is that even for a single algebra, right, we can talk about three forms. If it's a three-dimensional algebra, at least it could support a three form, right? Because we could have a d zeta wedge d zeta bar 2 wedge d zeta bar 3, that kind of thing. I'm going to stop fussing with that for a second. So I mean that's one. I don't even know what more to say there about that right now. It just seems like a large organizational mess for me at the moment. But I think it makes sense to take exterior derivatives. Right, and I would assume that we still have the same Leibniz rule, right? Like if we were to take d of alpha wedge beta, it's still going to be d alpha wedge beta plus minus 1 to the degree of alpha, alpha wedge d beta, right? I would assume that that's still the case. Just the algebra functions right along. And then the thing that we're most interested in, of course, is if we were to look at a surface, right, inside the, or let's say a submanifold of the algebra, right? And suppose this was a K-manifold. So here SK is some sort of K-dimensional surface inside the algebra. Obviously K less than or equal to N. Then what can we do? We could look at the form, the K form, alpha, right? Well, let's say a k minus 1 form alpha. Look at d alpha there, right? And then I'm assuming, I'm pretty sure we could work that out. That'd be the integral over the boundary of that k manifold of alpha. I do think that that's still gonna, ride along with these algebra coefficients. Alpha being a k minus 1 form. Again, I guess to make this really kind of interesting, you need a 3 or more dimensional algebra to really see things that are kind of neat, right? Because if we work with hyperbolic numbers, what are we looking at? An area integral, a line integral, that's it, You need something like a 3 hyperbolic or higher to really appreciate that, to try to study that theorem, what it means or tells us. I don't know right offhand what that would tell us. But I'd like to find out. So anyway, a direction for future fun. And by the way, guys, I'm not saying that this hasn't been done in certain contexts. Certainly it has been done in several complex variables with care by a lot of people, even in required courses. But I don't think that if you ask the same questions over an arbitrary associative algebra, that it's widely known or perhaps has been done, really. Now, saying it hasn't been done, that's kind of a claim on my part, but I'm not sure anyone knows, honestly. Has it been done by a Russian behind the Soviet curtain at some point? It seems entirely plausible. The Iron Curtain, I should say. Let's see here. All right, going back to... So at the top of my homepage, I've got those papers linked, So I wanted to talk about the second one, Theory of Series. Now, in terms of publications, I'm still trying to figure out where to try to publish this thing. The last section in here, I split off the last section in here, and I'm submitting it to a, what on earth? Submitting to something called the, what on this stupid light? The so-called pi mu epsilon journal. Because it seemed like a, decent place to send that last section, but the last section kind of, I realized I could talk about the last section without talking about, a calculus per se. So I just kind of split off the last section. It's its own thing, the result in there. It's a result derived from a calculus, so it seems like a decent thing to split off as its own paper and just kind of hide the a-calculus's technical background. But it is the natural outgrowth of this, and it is something that Daniel Fries noticed. Daniel, in like 2015, I asked Daniel, I was like, all right, so we understand calculus 1 more or less, but I don't know what's waiting for us in calculus 2. Like, can we do algebra? Can we do calculus 2 over an algebra? So what I told Daniel was like, so go to Rudin, baby Rudin, and try to go through it. Try to take the proofs in baby Rudin. Can you adapt them to functions, a-differentiable functions, the natural concept of sequences and series and so forth over an algebra? And that's what this paper is Daniel adapting Rudin and a couple, and I think also Johnsonbach and Pfaffenberg, or whatever that book is. It's a popular Dover book, one of the most popular ones. Pfaffenberger, I can't say it right. To the calculus. And so this is what happened. So we've already gone over this, what's an algebra? We know that, right? Left multiplication maps, right multiplication maps, your regular representation, With or without a basis, all that good stuff. There's your regular representation of the complex numbers. There's your regular representation of the hyperbolic numbers. Sorry, I still have not read Mater and Rosa. Some point, Cooper, at some point. I'll talk about that. Sorry, it's not happened yet. So this is just like a really brief best of the previous stuff from last paper. Of course, we don't have a multiplicative norm. We have a submultiplicative norm. And at the point I wrote this paper, I only knew that you could put a root 2 here, and I have a geometric proof of that. I was very happy last class for King to provide us with a proof that, in fact, if you look at the n hyperbolic numbers, we can put root n there, which is nice. Definitely an improvement over what's here. And when I use m sub a in this paper, I'm not using it in the sense that Kang used last class, in the sense that he said it should, he wanted to introduce it as being the best one, the inf of all possible m sub a's, which is good. But that's not always the sense in which I use it here, so beware of that. Of course, that exists, so you could use it, but anyway. I don't want to be responsible for calculating it for an arbitrary algebra either, because that's kind of, well, you've experienced that, Kang, right? It's bad. It's bad. Like, even one of those questions makes a decent undergraduate research project, right, if you think about it, right? You pick a sufficient, like a 6-dimensional ugly algebra, and you can ask a Calculus 2 student who's looking for a hard math problem, find m sub a. It's something that if you talk to them for a few hours, you can explain, even though they don't understand a differentiability, they don't have an abstract algebra background, they know nothing. All they know, there are these equations that define it, and your goal is to find the best estimate. That is a problem you can assign to a math student at any point, and that's why this is a good undergraduate research topic, because it's got all kinds of things like that if you just start looking. I think that's nice that you can do that, but now you could debate whether or not that's interesting. It's not interesting to me at the moment, but anyway. So, of course, I proved this bound for m sub a in my first paper. And then this took me a while to come to, but finally it dawned on me that if we have that submultiplicative constant, and if you have a unit, then you can prove that the quotient of the norms has to be less than or equal to m sub a of the norm of the quotient. That was missing from my analysis for a while. Once I found that, that opened a few doors that I should have seen that earlier. Here's a shout out to the thing I haven't talked to you guys yet about D1 versus D2 differentiability. D1 is the notion that I use. This is the Frechet differentiability paired with the assumption that the differentials in the regular representation of the algebra, that for me is a differentiability. Lots of authors who study commutative algebras, calculus over commutative semi-simple algebras, they'll use this other definition. They'll use a deleted difference quotient. So what they do is they take the limit of, they don't take this, they take the actual difference. You've seen this in complex if you took it. We look at, the regular difference quotient a la calculus 1 and take the limit as the, h goes to 0. That defines, for example, f prime of z would be f of z plus h minus f of z divided by h. You take the limit as h goes to 0. That defines f prime of z. That's the typical definition given in a complex course. And that actually, with the proper kind of massage, will make sense for things like hyperbolic numbers, provided that in that limiting process you throw out zero divisors. So you take what's called the deleted difference quotient. That makes sense because the non-zero divisors are dense, or the units are dense, so you're taking the limit over a dense set. It makes sense. Topologically, you can take such limits. And one of the things I showed in the first paper is, in fact, that there's no distinction between these concepts over an open set of a semi-simple commutative algebra. That I could use difference quotients or I could use my typical A differentiability, doesn't matter. We get the same functions in terms of A differentiability. However, I also showed that the deleted difference quotient's not great because for nilpotent algebras, you have functions which are everywhere A differentiable and yet are nowhere deleted difference quotient differentiable. So the deleted difference quotient idea doesn't work well for nilpotent algebras, which is something I'd like to consider some. So again, the deleted difference quotient has the advantage of more syncing even more strongly with basic undergraduate Calc 1 audience, you know? I'm not that interested. Anyway, so there's your Cauchy-Riemann equations, right? So moving along. We had our properties, you know, sum, pull a constant out, product rule, chain rule. We can characterize. We get the power rule. We can characterize Cauchy-Riemann equations by the vanishing of all the conjugate variables, as I've talked to you guys about. We can define higher derivatives by iterating lower derivatives because we can identify the derivative with, we can identify a differentiable linear, we can identify right linear transformations on the algebra with algebra elements. And so we can define the derivative as a function on the algebra as opposed to a differential operator on the algebra. And so we can define second derivatives and higher derivatives also as functions on the algebra. Yay. And of course, that ultimately leads to the penultimate formula, which is that for a multiply differentiable function, which is at least once a differentiable. In fact, it's k times a differentiable. And more than that, the k-fold partial derivative can be replaced with the k-fold multiple over the algebra and just the first derivative, assuming that one is the unit variable. And so that gives me this wonderful theorem, which is that algebra equations convert to partial differential equations naturally over the algebra. I still don't think I've fully exploited the power of this observation. I think that has much more to apply. But anyway, I digress. And then I also got a Taylor's formula. So you can, for an adifferentiable function, there's a multivariate Taylor's formula, and you can trade the multivariate formula for just a product in the algebra. There's more to this than it first appears. Like if you go back in my first paper and look at the proof of this, it's really quite neat the way that worked out. And shout out to Zorich for giving me the multivariate real thing to build that onto. Anyway, I digress. So, and then as we talked about last time, the mammal theorem, the integrals, and Cauchy integrals, finally leading Cauchy integral theorem. There we go, new material, finally. All right, I take my time in this paper, getting to the new material, page 9. Goodness gracious, I'm never going to publish this thing. All right, so what's a sequence? A sequence is a function from the natural numbers to the algebra. This is not surprising, right? Convergence of sequence is measured in terms of the norm. So what do we mean if we have a sequence in the algebra? It's said to converge to a point if for every epsilon greater than 0, you can find an integer m such that beyond m, you have that the distance between the sequence and the limit point is less than epsilon. Nothing surprising here, right? Okay. So here's a token example. He's got Pn is In plus 1 plus I over n. And he shows that that is less than that. And so he shows basically that this thing limits to I. So there you go. Exciting. So here's the first theorem. And the theorems are pretty, the results for the theorems are completely unsurprising. The only thing that's really novel in this part of the paper is proofs. The proofs are modified from Rudin because we have to deal with the submultiplicativity. And sometimes that's a bigger deal than others. Sometimes it's really not that big a deal at all. So anyway, if you've got a pair of algebra valued sequences, and I also need to assume that I'm working with a basis so that the ith component of the basis is less than or equal to the norm of the whole thing. You can consider bases where that's not true, but I refuse because those are unpleasant. Well, let's just say that if you work with a basis where the component can be larger than the norm of the whole vector, it's very awkward for the analysis. I mean, you can always find a basis where that's not the case, so you might as well work with such bases that the components for the length of the vector are all smaller than the total length of the vector. To have that not be the case, you have to conspire to have a basis that goes like this, and to have another one that goes like this. So you have like length almost 2, but the net length of the vector is like epsilon. So that comes from vectors kind of like the basis being unnecessarily like, anyway. This is a relatively mild assumption on the basis. I'm going to make it. So I got sequences which converge, to Sn and Tn, I think. No, those are just the partial sums. The limit of Sn is S. The limit of Tn is T. All right. And so these are actually series, aren't they? This is actually the limit of partial sums, right? And so the limit of, this says the limit of a sum of series is the sum of the series. This says that if you take alpha times the series, you get, you can pull alpha out of a series that converges. You can, you only get that the series converges if every component of it converges, because the series is, after all, a vector-valued series, because the algebra is, vector space. And finally, this one actually requires kind of a little bit more nuance, but the limit of the product of Sn and Tn is equal to S times T. Oh, I'm sorry. I said that these are series. I'm wrong. These are not series. I'm an idiot. I got distracted. This is not a series. This is just the component breakdown of the sequence. The series stuff is later. I'm an idiot. Oh, I'm sorry. Right? Those are not infinite. That's just a breakdown in the basis. All right, anyway, moving along. So the proofs are not especially exciting to me at the moment. You can read them. I will show you that the product one is a little fussy. I mean, I look at the difference, then, expanding on the basis, we get that. And then, I had to use the maximum of the structure constants, and the n is the dimension of the algebra here. So, and then this calculation's in Rudin, so I still had to play that game. If you've never proved the product of the sequences is the product of the limits, then this might be surprising that it's this complicated to you. But it gets more complicated over the algebra due to the submultiplicativity. In particular, I get this, and then that breaks to this, which breaks to this, which breaks to this. And then we look at these 4 n's, one that does that, one that does that, one that does something I haven't shown yet, another one that shows something I haven't shown yet. You pick the max of all these, right? You pick the max of all these so you can have your cake and squeeze it too. And squeeze all these things, squeeze, and limit, control, and eventually you get down to epsilon. Yeah.
Also, this kind of proven sum, but way short.
What's that?
I mean, I also did this kind of limit of the sequence in the sum.
Oh, you have a much shorter proof of this?
Yeah.
Ah.
You just look at this terrifying.
This is a terrifying way to do it. Well, I helped him, so that's probably part of it. It's probably my fault. I think he had a shorter proof, and I made it longer. So maybe his shorter proof was right, and it was your proof, and I talked him out of it. I don't know. Yeah, I wouldn't be surprised if it could be improved. I hope it's correct, but minimal, maybe not. It'd be wonderful to actually have a referee to look at it and help me, actually chop out things that should be chopped out. But Anyway. This is pretty standard stuff. We can either deal with an epsilon delta limit or we can deal with a sequential limit. So we still have that freedom to go one way or the other. This I have I've sent this to a journal after this, and when I send it to a journal, I just cut this out entirely because it's really not a calculus at all. It's just the intended audience here includes undergraduates who may or may not know about this technique. All right. Then that brings us to the Koshu criterion. So you guys have had real analysis or taking it. So Koshu criterion says that, if we go far enough out, we can make terms as close together as we like, essentially. So Cauchy, if every epsilon greater than 0, there's some m such that beyond that big M, the difference between terms is less than epsilon. That leads us to the Koshu criterion, which says that if we have what? Convergent if and only if Cauchy, right? So that's useful because Cauchy is easier to show than the definition of convergent for many problems. So we use that. If A meets the Cauchy criterion, we say it's a complete algebra. Pretty much I only work with complete algebras because, well, we're essentially working on Rn with the standard topology, and that's a complete space. So, but even for non-commutative stuff, we can get completeness, like this trace, the Frobenius norm on the n by n matrix algebra is a complete algebra, for example. I use the Cauchy idea there, for example, to prove the convergence of the matrix exponential. You may have seen me do that at some point. All right, series. So as usual, we define a series, a numerical series, in terms of the sequence of partial sums, right? So this is defined to exist only if the limit of the partial sums as n goes to infinity exists. And otherwise, we say it diverges. We get a Cauchy criterion for series, which says that the series converges if and only if you can basically make the tail. Well, let's see, how is this? It's not exactly the tail. It's like, what is this? This is kind of like part of the tail. So between m and n, I guess it's the tail, essentially. So you can take any piece of the tail out to infinity. You can make it as small as you want. I mean, that's what this says in words, right? The integral, the sum, rather, from n to m can be made less than or equal to epsilon, right? For arbitrary m and n beyond some big M. So that's the Cauchy criterion for series, often useful. Nth term test. This should look familiar. In fact, to summarize this section, what we learn in this section is that the usual tests for numerical series still transfer to the algebra. Series are not that weird. Numerical series still behave pretty nicely. We have nth term test. We have the comparison test, right? If it's larger than a divergent series, it diverges. If it's smaller than a convergent series, it converges. I said that right, right? Okay. I have problems with this. If you have my calculus too, you know what I'm talking about. Kang knows. You can talk about absolute convergence, right? If you have, here's an example of something that converges, but it doesn't converge absolutely, because when you take the modulus, it becomes harmonic. Those things still happen. On the other hand, if we do have absolute convergence, that implies convergence. So that's nice. Again, the proof is by the Cauchy criterion, as usual. The root test. Man, I got so many things to prove in my online calculus too. I'm not allowed to make videos longer than 15 minutes. How am I going to prove these things in less than 15 minutes? I guess if I just take one of them and talk really fast.
Come to watch it at 2x speed.
2x speed?
Record your video for half hour.
Yeah, I think the lifelong learner folks learning my Calculus 2 online over the weekend in their 3 hours they study, it's going to work really well. Um, anyway, root test. There's a root test, and it says what it usually says. If the lim sup of the nth root of the norm of A is, if it's less than 1, it converges absolutely. If it's greater than 1, it diverges. If it's equal to 1, it tells you nothing. That's the usual root test. What else? Here's an example. Ratio test. Again, not to be boring, but same song and dance. It converges absolutely. If the lim sup is less than 1, it converges absolutely. If, on the other hand, this is greater than or equal to 1 for all n beyond some m naught, then it diverges. You can show that that quotient becomes larger than 1 beyond some point, then you get divergence of the series. The proof, let's see here, let's look at the proof of 1. So if that's less than 1, that means we can find a beta which is smaller than 1, such that this quotient is always less than beta. Then if we look at a sub m plus 1, that's less than or equal to beta a sub m, which implies that a sub m plus 2 is less than beta, which is beta squared times a sub m, which gives us that eta m plus p is less than or equal to beta p a to the m for all p. Consequently, a sub n is less than or equal to a sub m times that, right? And then I said it follows by the comparison test so comparison to what? Notice that m here is, the big M is fixed, right? So what am I comparing to? Why does this, this is a fixed number, right? And what are we looking at here? We're looking at a fixed number, beta to the minus m, times beta to the n, right? But beta is a real number, less than 1. So this is just a real number times a real number less than 1 raised to the n power. That converges because it's a geometric series with a equal to this stuff, and there's the radius. The radius is beta, which is less than 1, so it converges. So then by comparison, the thing smaller than it must also converge, the series. That, by the way, is the usual proof too. So it doesn't seem like the submultiplicative trouble has not come upon us yet. You're going to have the sum of the series is the series of the sum. You can pull constants out of a series. All right, it's all good. The product of series, the Koshu product still makes sense. That requires a little bit more. Anytime you hit on products, you end up having to deal with a little bit more complicated argument, which probably could be made simpler if I had to predict something Kang was going to say. I try to find something that's correct. I'm not sure that minimal is what I'm after. That would require me being more awake than I am, I think. And
this one is just.
This one's okay.
It looks like.
This one looks.
With symbol n.
Oh, okay. So the other one had too many n's. You're like no. Okay, so anyway, the proof for the product involves some kind of like careful manipulations, but at the end of it, I still get the usual result, which is that if we have an absolutely convergent series and we have another series which converges, then the product of them, the Koshu product, is defined and converges. And it doesn't really matter if it's the left or the right one that's absolutely convergent. In either case, we're going to get convergence. You can see that this argument could be done either from the right or the left. And so I think that part of this section, I've thought a little bit about the non-commutative case here. I think it's fine. That's all I'm trying to say. Okay, well, now we're going to get to the weird part. Power series is where it all falls apart. Starts to really get weird. So what's a power series over the algebra? Well, we're going to have coefficients in the algebra, and then we have an algebra variable. I've been using zeta lately, but z minus z naught to the n, right? Coefficients in the algebra like that. So this is said to be a power series centered at z naught with coefficients cn, right? And lemma, of course, if you get that this thing converges on u, then you can define g of z like this to converge on z2 minus z1 plus u, right? So the point is there that I can just take the domain of convergence and I can shift it around if I want. You know, I can trade my z1 center for z2 center by just shifting the domain appropriately. This basically just moves points in u to points in this new shifted translated set. Long story short, I'm just trying to justify working just at 0. If we understand how things work at 0, we can always use this lemma to shift elsewhere. We also do this in calculus too, right? I mean, how many examples in calculus 2 did you center at something other than 0? Like maybe 10%, right? And there's a good reason for that, because why make things more complicated? All right, so, but I guess I do make things more complicated here for a while anyway, mostly just as a point of reference. If I was, teaching this as a more sort of extended thing, I think I might do this just centered at 0, just to remove the distraction of z naught or something. But okay, root test for power series. Given an algebra A with some multiplicative constant m sub a, and the power series, if we say alpha is the lim sup of the nth root of the norms of the coefficients, and the r is 1 over m sub a times alpha, all right, then this series is convergent absolutely inside that radius. Moreover, if alpha is equal to 0, then you have you could call the series entire. I mean, it converges on the whole algebra. For example, something like if you had your coefficients were n factorial, that would be the sort of situation that the alpha would work out to, 0. Something with nice, very convergent coefficients will work out so that your alpha is 0. Now, what's missing here? The root test we looked at numerically. See, in the regular root test for power series, there's another sentence which says that, first of all, the m sub a is nowhere to be found. It's just 1 over alpha. Second of all, it says that if you're beyond 1 over alpha, your series does what? It diverges if alpha is finite. Nothing about divergence here. Of course, also nothing about the boundaries. There's still all the fun stuff can happen on the boundary, just like in the usual case, but nothing about divergence here. And so the proof relies on the root test for numerical series, right? So we let a sub n be the product of cn zn, and we just try to calculate the lim sup of it. We calculate the lim sup. So the thing is, when we take that nth root, it pulls out an m sub a, like that. But then, if we look back at proposition 2.6 said that we can pull the n out like that. See that? That n pulls out to, see the n going out there? That creates an m sub a to the n minus 1 power. That's what proposition 2.6 says, is that we can, Now, usually you either, usually you just have something like, either it's equal, you just pull it out with equality if it's a multiplicative norm, or seems like there's some other context I've worked with where m sub a is essentially 1, but anyway.